Hello everyone, my name is Maria Cromida and I'm a PhD candidate at the Knowledge and Database Systems Laboratory at the National Technological University of Athens. I would like to thank you for being in the presentation where I will discuss a system for the visualization and exploration of big data sets based on semantic community detection. Before I go into details about the system and its architecture, allow me please to say a little about the motivation for this work. As you may know, nowadays, the volume of the IDF datasets that is currently available is constantly increasing. More and more datasets from different thematic topics become available, resulting in a plethora of people being interested in exploring them. The strict structure of the RDF dataset, however, makes it very difficult for people with limited or no knowledge of the semantic web to explore and understand this information. Currently, systems that aim to provide a solution for the exploration of these datasets focus either on the semantic aspects of the information or on the structure of the dataset. I present here today a system that takes into consideration both characteristics in order to support the exploration of the datasets. How this is achieved? The system is based on a client-server architectural design where the input dataset is pre-processed in order to be enhanced with the semantic information. Then the semantic communities are detected and visualized in the two-dimensional space. The final information is stored in a graph database and offered through an interactive visualization interface. An easy-to-use toolbox of functionalities allows the exploration of information even for users with limited knowledge about the semantic web. The preprocessing of the dataset is divided in three main steps. First, each RDF triplet is mapped to one node in a custom 3D space. The XYZ coordinates of this space are now the subject, predicate, and object of the original dataset. A complete graph is then created between these triplets. Next, the semantic weight between the triplets is calculated, which is achieved through semantic processing of the dataset. First, groups with semantically similar words are created, and each one is given a popularity score based on the number of words that belong to it. Next, the popularity score is used as a semantic similarity indicator for the words that are included to the group. Based on that, its label of the dataset is given a semantic score, taking into account the words it contains and the popularity of the group they belong. Finally, the distance between nodes is calculated using this semantic score for the three dimensions of the custom space. The third step of the preprocessing is the community detection. Leveraging on the calculated distance among the nodes, a proximity graph is formed by applying the direct minimum spanning tree algorithm. This is performed by joining minimum spanning trees from the full weighted graph. Next, this graph is embedded in the hyperbolic space, which means practically that now each node is assigned coordinates in a hyperbolic space, which is achieved using the Rigel algorithm. The centrality score or Hebect is calculated for each edge. The score reflects how central or bridge-like is an edge, meaning that high centrality scores are expected to indicate edges that when removed will lead to a disconnected graph. Based on that, edges are ranked in descending order of their Hebect values and removed until either the graph becomes disconnected, meaning that a new community has been detected, or a predefined number of edges has been removed. If the required number of communities is detected, then the process terminates. Otherwise, it is repeated for the largest connected component of the graph. This way, the communities are detected in the initial input data. As it was discussed so far, the input dataset is pre-processed in order to detect semantic communities. After that, in order to support the client-server model and the functionalities of the interface, two visualization layers are created. The first layer is the inter-community visualization, basically an overview of the dataset where the identified communities and the connection between them are included. The second layer is the intra-community visualization, which presents the triplets that belong to each community visualized as a graph in a two-dimensional space. In order to support the scalability of the system, the dataset is stored in a graph database. The detected communities are stored as metadata of the node of the dataset, and the special information for each node based on the intra-community visualization is also stored in the database. The user interface has been designed to support the exploration of the dataset. For this reason, it is divided into three main panels. These are the dataset selector, the functionality toolkit, and the interactive graph visualization panel. The dataset selector allows the user to navigate easily between the datasets. In this demonstration, we are focusing on two datasets. The first one is presenting some papers, the authors and the publication date, while the second one is presenting the social interaction between individuals. We start here with the overview of the dataset with the papers, and we see that there are three communities that have been detected based on the author, the title, and the publication date of the paper. The panel where the graph is visualized is responsive to zoom and panning actions, which you will see here as we load all the nodes of the graph. Note that on the initial overview of the nodes in the three communities, there are no details shown in order to keep the visualization clean, but as the user zooms in, more details are added about the nodes, including their labels or the weight of the edges when applicable. This additional information is also available when the mouse is over the node, and this functionality is available both for the detailed visualization of the nodes that we see here and the community overview. Next, we show that the inner community with ID 2 has been isolated, and this includes the authors that have published papers and then included in this dataset. For each author, we can see with the mouse over additional details. Next, we are performing a keyword search using the paper ID, and we see the related information about the paper. And the search is repeated twice, first using the paper ID and then using a keyword for the title of the paper. As you can see, we have again the same information, but it includes the co-authors of the paper, the title, and the publication date. In the next step, we change the dataset to the one showing the social interaction between individuals, and we see the community overview and the initial graph, where no communities have yet to be detected. Next, we focus on one node, and we select the node based on its name, and then we see connections up to first 1 degree, and then up to 2 degrees, as expected. As we add the path length, the graph that results from this query becomes more complex and provides more information. Next, we isolate the path between two nodes by selecting their names, and we can see how these are connected. Finally, we filter the nodes based on the age and the gender of the participants. And in these groups, as you can see, the colors of the communities are respected in this visualization of the query result in order to further support the user with their understanding of how they can explore the information. Thank you very much for your attention. I will be happy to answer any questions that you have now or the live demo session.